To our webinar on HiRISE. I'm Flora Zhu, a sophomore from Great Neck South High School, New York State. I am a student volunteer for the Planet+AI program. I will be your moderator today. Our speaker today is Dr. Sarah Sutton. Dr. Sarah Sutton is a research scientist at the University of Arizona. She's the photogrammetry program lead. She studies planetary surface processes on Mars, Earth, the Moon, Europa, and Io. Today's topic is on HiRISE images of Martian surface. This event is supported by the National Science Foundation and also by the Tennessee Space Grant Consortium at UT. And this webinar is live streaming now. Dr. Sutton, would you please share your full screen?
Sure, let me do that. I'll try this.
All right, I'll give it to you.
And you have done half my work for me. Thank you, Flora. Thanks for inviting me today. I really hope that people can jump in and ask me questions because I know that you're interested in AI, and that is not something I actually know a lot about, or how you would be interested in connecting your work to HiRISE topography data or photogrammetry. So please do ask me questions. As you mentioned, I am a research scientist. I do study planetary surfaces, including volcanism, geomorphology in general, aeolian processes, so dunes, which is a big research topic on Mars especially. I'm also interested in polar geology, change detection on planetary surfaces, which is surprisingly challenging, and I'll talk about that a little bit. And then I have done some work here studying terrestrial analogs where we can go and actually like touch the rocks here on Earth and then use them to understand what the processes might be similar on other planets. So in the very most basic description of HiRISE, which is the high resolution imaging science experiment, which is an instrument on the Mars Reconnaissance Orbiter. And here is a artist rendition of MRO orbiting Mars with HiRISE pointed out there on the instrument deck facing the surface. It's basically a telescope, a very powerful telescope pointed at the surface of Mars from orbit. It's been operating for over 16 years and has returned like a tremendous amount of data of the surface of Mars, but not a lot of the surface area. So when we say high resolution, we mean the trade-off is we have this powerful telescope with a half-meter diameter mirror and a detector width that's equivalent to like 20,000 pixels across, each pixel being nominally 25 centimeters. So this image on the right is a very, very early demonstration of how high resolution on Mars might correspond to what we might look at on Earth. And I know you are not here in Tucson, but this image is a picture, an aerial view of the city of Tucson with the campus of the university, kind of where the arrow starts, University of Arizona. And then this is actually the building I'm in right now from like 2008 when they were doing some construction on campus. So this is to demonstrate from a human perspective, the resolution capability. So you can clearly see cars, building edges, roads, trees, things like that. Of course, none of those things exist on Mars. So when we look at the surface of Mars, we wonder, well, what are we actually resolving? And this helps us put it in a human perspective. So HiRISE is a really complicated instrument. It is made up of 10 CCD detectors, fully spanning the swath width of the image in visible red light. So there's a filter on those. This is because red is the brightest wavelength that is reflected off of the surface of Mars in general. So we have the highest signal to noise ratio for the red light band in the visible band. And then we have this center swath where we actually can create a 3-band color with blue-green filters and a near-infrared filter. So these other 4 detectors span the centers like 20% of the image width. So the way HiRISE builds up images is as it's orbiting Mars, it builds an image line by line. So all of these detectors are imaging essentially, just think of it as one image line at a time. The way that all gets merged into the image is, complicated pipeline process, but you end up with a single image that is, as I said, about 20,000 pixels across. And we have a lot of imaging modes to optimize the quality of the images, but essentially we image at either 25 centimeters per pixel, or if we need to improve the signal, we can bend the data to get an effective resolution of 50 centimeters per pixel. So that's still very high. What this means is we don't image large areas of the surface of Mars. So I think we've imaged about 4% of Mars surface uniquely, maybe less than that. So we're looking for the most interesting parts of Mars. The thing I really spend my time on for HiRISE, besides various image processing tasks, is developing this stereophotogrammetry data. So that's a long word that essentially means we generate topography from 2 HiRISE images of the same location on the ground. And that requires some special targeting. So HiRISE as an instrument does not move. It cannot be aimed or pointed independently of MRO. The entire MRO spacecraft has to roll off nadir. So this little cartoon shows basically how that would, let me see, I see. There's a question in the chat, but I can't read it. So actually, if someone could let me know what the question is, I'd be very happy to answer it or comment.
We'll answer all questions during Q&A part.
Okay, great.
We only see first slide.
Go ahead.
Well, we can only see the first slide.
Oh, really?
Mhm.
Oh. You're not seeing me change the slides?
No.
Oh, okay. Sorry about that. That is good to know because I'm just talking away here and
Yeah, we are seeing another one.
Okay, I think I know what happened. Let me see if I can fix this. Hang on one second. How about now?
Yeah, it's working.
Great. Okay, sorry about that. Thanks for letting me know before I went on for too long. So the thing I was pointing at before was this is the image of, or describing, which you weren't seeing, was the image of the city with the campus and the buildings. So I hope that makes a little more sense now. And then this very complicated diagram, which I was describing to the Boyd, was this. So here we have this is a cartoon of the imaging construction, basically. So the image is built up line by line by line as the spacecraft flies over in orbit. So the line speed has to match the spacecraft ground track speed. So we're actually acquiring the data extremely fast, and we're limited in the length of the images by how much memory we have or how much the temperature ranges of the instrument during image acquisition. So the spacecraft rolls off nadir to point at a surface target. And then we have to wait until we can come around and image that same part of the surface again from another angle. And we calculate these angles and plan the image acquisition so that we can get a good stereo pair, which allows the image pair to be reconstructed in a way that we can estimate elevation. So the surface topography. So we can reconstruct a portion of the surface of Mars in high resolution topography using this. So this is what the stereophotogrammetry term encompasses. Stereo meaning two images, photogrammetry meaning making measurements on photos. So this is a map of the whole surface of Mars in a rectangular projection. So latitude is from the South Pole to the North Pole, and then all the longitudes. So the poles are extremely distorted in this map projection, but it's showing all of these stereo pairs that we've acquired. And these symbols are much, much, much larger than the actual image size, but you wouldn't see them if they were the actual size. And all the blue images, all the blue dots are stereo pairs that we've acquired. So over almost 8,000 stereo pairs to date have been acquired. And then of those, we have made, just over 1,000 terrain models. So you can take a stereo pair and generate an anaglyph, which you can look at in 3D with the red and blue glasses, like you do a 3D movie. But to create the terrain model that is digital topography model that can then be analyzed and manipulated in a lot of different ways and actually made measurements on, that's a much more intensive process, which is what I lead. And that's why there are so few of those relative to the number of stereo pairs we've acquired. So what does this look like? Here is an example of a stereo pair from HiRISE. And we would you can call it the first half and second half of the stereo pair, or the left eye and the right eye view. These are combined in a long, complicated process into a map. And this image here, that's the rainbow colored, is a digital terrain model. So that is actually a visualization of the elevation where color equals different elevation heights above the Mars mean elevation. So blue and purple are the lowest values, and the white is the highest value. And on the right is an anaglyph. If you have the red and blue glasses, you could look at that, but I don't expect everybody to have those at hand all the time like we do. So you do not have to understand this flowchart. It's just a kind of an example of how it's a very complicated many-step process that is not exactly linear and has maybe 2 or more iterations through this looping, multi-step, interactive and automated process. And we have highly trained people working on this. We do employ undergraduate students in my lab. We train them up, and they get to learn this process, and it's an incredibly valuable skill that has taken them off in many different directions in terms of graduate school and their professional careers after graduation. So that's something that's really good to be on the HiRISE team and also be at a university where we can work with students. Here's another example of some of the output products from this DTM production process. So these are all available to the public, and I will give you some links later. The image on the left is similar to the one I showed you, where it's the colorized elevation map with this next image here is the shaded relief. So that's basically the surface texture of the DTM with some artificial illumination. So that just shows you the surface. And then when you combine that with the color, that gives you an elevation map. This black and white image that looks sort of like an X-ray is another way to visualize the elevation, where it's just grayscale, where the darker shades are lower elevation and the white is the higher elevation. Then we produce a quality map that comes out of the software we use, which gives us, provides the user with a knowledge of where the elevation model is reliable, which is the sea green color, and where there might have been some interpolation, which are these yellow and orange areas. And then there's some turquoise areas that are manually edited. And so and I'll talk about that a little bit later too. And then on the process, when you create the terrain model, another really important product that comes out of this is we reproject the image, the source images, onto the terrain model, and that's a process called orthorectification. And we do that for that center's color swath too. So you really, really need to connect the ortho images to the DTM to use them together to be able to make accurate measurements on the images. This is a really key point. Another sort of special product we can do, there's a second comment in the chat. Please yell at me if there's something like really important missing, or like my screen isn't changing or something like that. Let me know. I'll carry on. So the special products we can make are mosaicing multiple stereo pairs together, which is even a little more complicated than just making one DTM. So this is showing how we can extend the coverage of our HiRISE high resolution topography by mosaicing multiple stereo pairs together, which is a real testament to the planning quality of our uplink team, and the skill of our DTM producers. And as I mentioned, many of them are students and start out as students. This schematic here is showing how we undergo this process, or we put the images through this process that's generically called bundle adjustment. Kind of a technical term, and basically it means we're tying all the images to each other to match them up, because they don't start out perfectly matched up with each other in this, even though we've targeted them at the same place on the ground. And then we control the matched up images to the global topographic reference data set. And that was acquired from another instrument that flew on a different spacecraft. And the spacecraft was the Mars Global Surveyor, and the instrument was the Mars Orbiter Laser Altimeter. So it actually fired a laser beam at the surface of Mars, like millions and millions of laser shots to detect the surface heights. And then those laser shots were all combined into a global data set. And the center panel here is showing how our terrain model compares to the reference laser altimetry data, which are represented by these yellow and orange and green dots. They look like lines, but they're actually individual dots representing each individual laser shot. It's kind of a complicated topic. I'll be really happy to answer questions about it if you have more of them. But the essential story here is that we're fitting a very high resolution optical image data set to a much, much, much lower resolution, but very precise laser altimetry. And so we're looking to get our topographic models to match the reference data within 5 meters in the vertical space, 5 meters of elevation. And this is an example showing that we do a pretty good job of that. So why are ortho-rectified images so important? Let me make this play. This is a 3-pane animated GIF of dunes moving on Mars. So we have a scale bar up here in the upper corner that says 50 meters. So that's your 50-meter scale bar. So these dunes are very large. And you'll notice that they're moving over a period of 5 Mars years, which is about 10 Earth years. The ground between the dunes does not move. That is because we're using a sequence of images that have been orthorectified to the stereo pair. And that is a process that is very challenging to do. But when we can do it well and we can achieve a very good control, as in this example, that allows scientists to make very accurate measurements of, say, the motions of dunes without any other perspective view distortion. And you can make pixel to pixel comparisons from images taken very far apart in time or close in time, depending on what your goal is. So this is because MRO has been orbiting Mars for so long, we're able to build up these data sets of monitoring sites where we can look at changes happening on the surface of Mars and start to make some very rigorous and quantitative measurements of how these features are moving or changing. And that it really informs our understanding of Mars's climate and geology. So this map is, again, the global map of Mars, and it's showing, it's now a little bit out of date, but all of the small orange dots represent where there's a DTM on the surface of Mars. And then the circle size that is larger than the small circle is symbolizing, and again, the symbols are all much larger than the actual DTM footprints. Those circles with the numbers are indicating how many orthorectified images we have generated over specific sites. So in some of these, we have 30, almost 40 images over one location. And that's where we're looking at changes that we know are happening, and we continuously target them to get monitoring images, and then we orthorectify them so that we can create these basically change detection maps. And it's been a very revolutionary sort of data set that we've been able to learn a lot about a lot of active processes on Mars. So sometimes the perception is that Mars is a dead planet because there's not been any detected life on it. But as a geologist, I would disagree with that, because there's a lot of seasonal activity, annual activity, and a lot of changes happening on Mars. So we can see geology in action. It's not static, let's say that. Another benefit to using these topography models is for assessing candidate landing sites. So I'm sure that you've all heard of the rovers and landers that have been successfully operated on Mars by NASA and other countries. And one of the first things to selecting a good landing site is to basically acquire the best data that you can over that landing site. And one of the important data sets is the topography, because you don't want to land your spacecraft on your rover or your lander on a hazardous site that's full of boulders or full of steep slopes or other dangers. So this is just one example of a really incredibly boring, landing sites they tend to be safe, which might be boring geologically, but they selected this landing site in particular for many reasons. But this is the InSight lander, not a rover. And they wanted to land it in a very specific area. And these green polygons are individual HiRISE DTMs rendered as slope maps. So they're looking at the surface slopes, and they wanted slopes to be within, below some threshold, like 10 degrees or something. And not that the InSight lander was going to move about, but that they were looking for specific safe landing areas. And this landing ellipse is mostly covered enough so that they could determine this is very safe. This is just one example. There are, of course, many, many other candidate landing sites that have been analyzed with extensive amounts of data. Another thing that I really work on in my work is understanding the quality of the terrain models, and then conveying that to the users in the scientific community and to other users of the data, looking at it for engineering purposes or visualization purposes, or when you see artifacts, what do those mean? So this is a kind of complicated figure looking at two DTMs. So they're overlaying these two, and then where they overlapped, we could create a difference map. So that's basically subtracting one model from the other. When you subtract elevation values in one DTM and the elevation values in the other, and you look at the differences between the two. The goal of this effort would have been to look for surface changes. And this is actually pretty hard to resolve on Mars because only in the case of those like very large dunes that are moving many meters over the years can we resolve surface changes with confidence. But in other parts of Mars, like there's gully erosion and this is a South Polar ice-rich feature they call araneaforms or spiders, looking for active surface processes that actually change the topography. The change has to be larger than some certain threshold to be measurable in the two terrain models. And that's basically, I'm trying to explain here that there's how to measure and combine the error in both models to know whether or not the differences are due to just intrinsic noise in the terrain models, artifacts, or actual changes in topography. And I tend to be the more skeptical person about detected changes. And so this green and blue lines that say A to A prime, which is drawn across, shown what the image feature looks like where the profile lines are drawn. You see a lot of differences, but does that mean that actually the surface changed, or is that just the models are different because of all the different factors that go into it? And then the maroon plot in the bottom right shows the differences compared to the vertical precision with sort of error bars. So like you'd really have to exceed the light gray area to be really sure that that was topographic change. So generally, though the vertical precision of the models is within tens of centimeters, so they're excellent, but you have to be careful when you're analyzing them, just like any topography data. And the accuracy, this is again an image that I showed before, and I talked a little bit about how we compare our models to the global topographic reference data from MOLA. And then our horizontal resolution, I mentioned that our source stereo images may be 25 or 50 centimeters per pixel, but the DTMs are created at what we call, I know there's a lot of words I'm using, pixel, I'm using resolution, and now I'm going to throw in another one, GSD or ground sample distance. That's basically the horizontal spacing of the grid of elevation values. So in the DTM, because they're digital rasters, that's a pixel, but you might see the term GSD sometimes used. So that's about 4 times. You can resolve elevation changes about 4 times the GSD. So we can resolve horizontal elevation changes at 1 or 2 meters. Still very high resolution for another planet, the highest resolution data for another planet. There is a lot of effort that goes into validating the quality of the absolute elevation and horizontal location of data sets like this, especially when you're talking about characterizing landing sites for robotic or human exploration. So I'm not going to go into that, but it's just a topic of interest, and I don't know if that's something that would fit in with what you all are interested in. So I talked about artifacts, and one of the reasons, and these are flaws, basically flaws in the DTMs. The main reason that we would have such artifacts in HiRISE images are because of this push broom imaging mode it does, where, as I mentioned, it's imaging very high speeds with these very small, like a small area of the ground. So any small motions or vibrations on the spacecraft as it's in flight can cause the camera basically to shift around while it's acquiring the images and building it up, and these cause distortions that we just call jitter. So I have spent quite a bit of time working on processing techniques to mitigate this effect in HiRISE images. And we came up with a solution to back out the frequencies of the spacecraft jitter from the image data and then apply a correction to the images that definitely improves the quality of the DTMs and minimizes these artifacts. But you will still see some show up because we can't remove it entirely. So things you might see in the terrain models, and these are all shaded relief images, which, as I said, are illustrating the surface texture. Not the elevation values, but the surface texture. And they kind of are meant to bring out the flaws, to show the user where to look out for. So you might see these long lines that sort of crisscross at angles. Those are jitter that causes a little bit of offset along the CCD seams. You might see these boxes of sort of noise. It's a tiling effect where there might be some Y parallax that causes some poor correlation qualities. You might see some factors like these sort of Pringle or Dorito chip or triangle looking facets that may be due actually less to jitter and more to, say, featureless areas on the surface. Dunes, because they are also very smooth and featureless and sometimes moving between stereo pairs, might also have artifacts where you have some large chunk of terrain that didn't resolve. So this is not real topography, it's an error. And we try to edit them out, but often that's just too time consuming. So we will selectively edit areas of high interest to the scientist requesting the data and maybe leave others untouched. You may see in panel E, you may see like large interpolated areas that are generally where in the images there are dark shadows and there's not enough information to reconstruct the terrain. F is showing jitter artifacts due to high frequency jitter where you get this sort of ripple effect, looks like a washboard. Usually that is low enough amplitude to be not, to not make the model invalid, but it's just good to be aware of. And then here's again those seams. And then here are some large scale, like not large, but blunders due to shadow differences. So I did mention that we can't acquire the stereo pair at the same time. We have to wait until we come around to another orbit. And that can lead to differences in illumination. And when the shadows are different shapes and sizes or lengths, the stereo matcher kind of like loses its mind. So these are things to look out for. The other thing about HiRISE is it's an aging instrument. Let's see. Yeah. Like I said, it's been in flight it's been operating for, I think, over 18 years, if you include when it just arrived at Mars. Maybe some of you weren't even born when it was launched. So over time, electronics wear out. Fortunately, this can have, this is something we just dread, but we have to do everything we can to mitigate it. In 2011, we lost the red CC9. So this cartoon is not to scale, but this is the detector layout up in the upper left. Red 9, which was on the edge, dropped out in 2011, which didn't really create any noticeable effects in the images because it was on the edge, thankfully. So we lost 10% of the image swath width. Last year, we lost red 4, and that was a much bigger effect because it's right in the middle of the image swath. So this white box is outlining the potential full width of a HiRISE image with the 2 gaps now. But because we have this overlapping IR data, which is in wavelength close enough to the red visible, even though it's in the infrared and not invisible light spectrum, for most areas on the surface of Mars, it's near enough visibly to match well enough to be basically laid over this gap here. So we can take this IR10 detector data and basically stuff it into where red 4 used to be and create, again, a continuous image. but we lose half of our color swath. So that's what's showing here in this map projected image. This, of course, affects DTM production strongly, and we're actively working on mitigating this today. Like I'm still working on this right now, but we're getting all the methods in place to replace the data. And as I said, IR is close enough to the red so that the terrain quality is very similar. It's essentially the same. So that's kind of a relief that we didn't lose a different CCD that we couldn't replace with something else. But we kind of know this is inevitable. So we may see HiRISE images shrink to about half their size in the coming years. So with that, I'm just going to end up with some links to show you if you're interested. uahirise.org is our homepage. hirise.org/DTM takes you to our DTM list. This is on the right showing you a detail page. Oops, sorry. I think I just dropped out. But the, I don't know how I did that. The other thing I wanted to mention is that we have another program called HiWish, and you can link to that on our website. And HiWish is a targeting tool for the community to use. So anyone can go on there and create an account, which is just basically your email, and target areas on Mars for HiRISE to take images of. So I think I stopped sharing, and I will be happy to take your questions, and I hope you have lots of questions for me.
Dr. Sutton, first of all, thank you for your amazing presentation. We enjoyed it a lot, and we have some questions in the chat and also on YouTube. So let's move
Great.
on to the Q&A part. The first question is, what is the difference between photogrammetry and 3D model?
That's a good question. I would say photogrammetry is using photos, which our models are not technically 3D. They're really 2.5D. If you think about it, if there's a overhanging image, overhanging topography, we can't create that in a 2.5D model. So we'll have like a surface that then just drops off and then continues. A 3D model can be represents truly 3 dimensions, and that's typically in our field discussed as a point cloud, where the object is represented by a collection of points. Each point has a X, Y, and Z, or a vector representation. So you can definitely describe a fully 3D volumetric space with a point cloud. The DTMs that we do with photogrammetric methods from optical images cannot do that the way we can do from orbit. Like we can't do that from orbit.
Okay.
So it's not quite 3D, it's 2.5D. That's a very good question, nuanced.
Thank you. The second question is, would you please comment on what AI can do for photogrammetry in planetary science?
So that is a good question, and I'm kind of hoping you all can tell me more about that than I can tell you. It's kind of a new topic to me, and I am really interested in exploring this, but I'm not sure what the tools are yet. As far as data processing, I am feeling pretty confident that in the near future, computer vision will advance to the point where it can reliably do a better job than we can as humans. So when I started doing this many, many years ago, we focused on this interactive method because the human operator could see the ground where we have the 2 images together more reliably than the stereo algorithm in the software. It worked most of the time, but then sometimes we needed the human operator to intervene and like make these corrections. So that is a very tedious process. And I hope that AI can, I know there's a lot of machine learning techniques and computer vision algorithms out there already, and there's huge advances being made all the time. And that's one way I think AI could be a contributor. The other way is I think a lot of people are working in my field, not myself particularly, on image segmentation and also identifying features. So throwing in all these, we have so much data now from planetary missions, particularly MRO, that we have the ability to, we have more images than we can process, like as humans. So counting craters, identifying where dunes are, or looking for specific features, or, just mapping. I think machine learning and AI has a lot of potential here. Like, say you know what a feature looks like and you want to like find it in all the HiRISE images. Well, there are like 40,000 of them more. So how are you going to do that there are not enough undergraduate students in the world. So I think that's another way that it could be very useful. I'm sure there are other ways. I'd be really interested to hear more about that.
Okay, thank you. Our next question is there any spacecraft which failed landing on Mars?
There are many.
Okay.
Mars is hard to land on, and our many attempts failed for quite a while. It's kind of a graveyard of spacecraft. They were NASA missions, a mission from the UK, Russian missions, European missions, but there are now a lot of successes. So I won't list all the failed landers, but HiRISE has been instrumental in actually locating some of the locations of missions that didn't successfully land. So that's been kind of fun because it's the only camera capable of resolving that sort of impact on the ground, so to speak, or spacecraft on the ground. And we do actually actively image the successfully landed missions to help them in their mission planning. So yeah, landing on Mars is very hard.
All right, thank you.
Mhm.
And next question is, what software do you use for photogrammetry?
We use a software, it's a commercial software called SocketSet. And we're transitioning to its next version, which is Socket GXP. That's not the only method. That's just the method that we have employed because of the quality of the data and our ability to interactively edit. There are other freely available methods that are automated. One of those is called AIM Stereo Pipeline. And that uses another free software for image processing from planetary data called ISIS. So those two software packages are freely available, and you can generate terrain models at home. It's a little bit of a learning curve, but it's all automated. But the software we use in my lab is called SocketSet.
Okay, thank you for sharing. Our
Mhm.
last question is HiRISE going to die in the future?
We hope not. The real limiting factor on the whole mission is MRO, the spacecraft, running out of fuel, or the batteries on it dying. So MRO is using solar panels to generate power for the spacecraft and to charge the batteries when it passes around the other side of Mars every day into the night side. Fortunately, the battery life is good and the fuel has been lasting. So we use the fuel to make orbit maneuver corrections to keep the spacecraft from deteriorating and landing on Mars, or crashing on Mars, I should say. So I believe we have 7 or more years of fuel left. So as I mentioned, the HiRISE instrument is undergoing some degradation as it ages, and that is due to constantly cycling electronics, which creates temperature. It heats up, it cools down, it heats up, it cools down every time it takes an image, and every time it passes through the night side of Mars. So that creates fatigue on the instrument. Now we have redundant electronics on the spacecraft and the HiRISE instrument, but we try not to switch back and forth too much. And the detector plane itself there's only one of them. So we don't know how long it will last. but we take great efforts to prolong its health as long as, hopefully longer than MRO mission. But you can see it's a struggle. It gets more complicated. Those are really good questions. Thank you.
Thank you. That's the end of our Q&A part. Dr.
Okay.
Sutton, thank you for your amazing presentation on HiRISE images on Martian surface. I hope to see you again. Bye.
Okay. Thank you both. Thank you all.